around. Hello. Oh, thank you for saying where you are. It's cool to see where everybody's tuning in from all over the world. Anthony, are you ready to get us started?
Yes, I am. I am.
Wonderful. Take it away.
Okay. Good afternoon, good morning, good evening to all of you who are coming in to watch this Duolingo English Test webinar. This is the seventh one in the series, and today's talk is on automated scoring of writing, comparing deep learning and feature-based approaches. And this is a very hot topic, as you know. Automated scoring of writing has become reasonably popular and critical in language test development for scoring and interpretation. So we all want to know more about it. And our two speakers for today are Alistair Van Moere and Jing, and they are well known in the field, and they've been giving lectures in various parts of the world, but I'll still say a few words about them. Alistair is president of MetaMetrics, and he's also research professor at the University of North Carolina, Chapel Hill. He has extensive publications and leadership roles in the last 2 decades. He was the president at Pearson, where he managed artificial intelligence scoring, and he has authored more than 20 research publications on assessment technologies. And his colleague, Jing is the vice president of AI and product innovation at MetaMetrics. And she has more than 15 years of experience in test development, measurement, statistics, machine learning, and product development. And she is a frequent presenter on this topic as well. So I'd like to welcome Alistair and Jing to start their presentation. On to you, Alistair.
Thanks, Anthony, for the nice introduction. Thank you to Duolingo for hosting this event and inviting us here. It's really great to be here and talk to everyone about a topic that we're really passionate about. And we've presented variations of this a couple of times before. If you were at the most recent LTRC, some of these slides will be familiar, or the recent ALA conference in Asia, some of these slides will be familiar, but there's always something new as well. So please stick with us. Anthony introduced myself and Jing. We have another author to this paper who's not presenting with us today, but I would like to acknowledge Steve Latenzio, who's one of the machine learning engineers in our AI team at MetaMetrics. Just organize my screen so I can do this better. Okay. So let me just start by telling you a little bit about MetaMetrics and who we are. It may be a company that not everyone is familiar with, but we're based in North Carolina. That's where our head office is. We have people all over the US. We are known for test development, psychometrics, AI scoring of writing and speaking, and for one of our brands, which is the Lexile Framework for Reading. So the Lexile Framework for Reading is a reading scale, which has two kinds of things on that scale. It is a way to measure the proficiency of students reading. So we can assign a Lexile reader measure to students to tell us how good they are at reading in English. And then on the scale as well, we can put the complexity of text. And so a Lexile measure for text tells us how complex is it to read this paragraph, passage, or book. And when these two are the same measure, here we have a student who's 770 Lexiles, and a book that is 770 Lexiles, we can say that this student is well matched to this book. It means that when she reads this book, she'll be challenged but not frustrated. So it's in her zone of learning. And since we've measured hundreds of thousands of books and millions of students, we have a nice ecosystem where students are being matched to books and it facilitates their learning. We work with all kinds of assessment partners some of which you may have heard of, but all of these report out student Lexile reader measures to their students. And we also work with content publishers and publishing partners who either measure their content and books and report them on the Lexile scale, or act as data aggregators and librarians. We have quite a global reach. Students in 180 countries have received our measures, more than 600 publishers. Over a couple of decades, we've measured more than 100 million texts, and every year, 35 million students receive a Lexile measure. So we have quite an impact on the education field. And today, just let me home in and say we're talking about AI scoring for writing, although we do plenty of other things at MetaMetrics, but we'll be pulling in some of the other things while we're talking. So I'm trying to put this in context. The agenda for today. So first, I'll give an overview of feature engineering versus deep learning models. Okay, so I'll give that general overview. Jing is going to take over and apply both approaches to data sets, and then we'll talk about lessons learned. So that's the idea. Let me start off with feature engineering. So I think this should be a fairly familiar process for most people. Basically, it's a way to extract features from text, right? Map those features to construct relevant traits, for example, in a rating scale. And then we build a statistical model to predict ground truth. What is ground truth? Well, sometimes it could be human ratings of how good that essay is. I put my tongue firmly in my cheek when I say that that is ground truth. Sometimes we don't know how good those human ratings are, but sometimes that's all we've got, and so we'll call that ground truth. So let's give an example of feature engineering in this context. Let me ask you the question. How would you make an algorithm that predicts text complexity? Like, what would you need if you wanted to do that? Well, I think you'd need two things. First, you'd need that ground truth. So you'd need to know which texts, which paragraphs, which passages are harder or easier, and by how much. And then you need to have a set of features that you can extract from those texts to predict that ground truth, right? Their complexity. And so when you've got those two things, you can build your algorithm. And I'm going to show you how we at MetaMetrics built one of our text complexity models. So we started off with 350 texts. You can think of these as 350 passages or paragraphs of varying kinds of complexity, from A1 through to C2 on CFR. Well, actually, this was a constrained set. This was more like A1 through to B1. And it's also the kinds of texts that first language learners might encounter in first grade, second grade, third grade, fourth grade. We had those texts evaluated by 90 raters. So they took a paired comparison approach where they were presented two texts side by side and they said, this one is harder. And then another two texts were presented side by side and they said, this one is harder. So 90 raters evaluated all 350 texts, and we were able to rank order those texts by difficulty. We also had students who took comprehension items on those texts. So we were able to find out how well did students understand those texts. And by aggregating all this data together in a RASH model, we have an empirical text difficulty for those texts. So for each of those 350 texts, we can say we know how difficult they are relative to each other and how difficult the students find those texts as well. So that's our ground truth. We then said, well, what are all the things in texts, these texts, that might predict their complexity? And we came up with this list of 22 features that might predict the complexity of the text. And for each of those features, we have multiple operationalizations of them. So we would take the means, the standard deviations, the ranges, and various other permutations of each feature, until we had 238 features in total that we thought we should evaluate to see how good are they at predicting text complexity. And then we put them in a statistical model. We actually put them in two statistical models. One was a random forest regression model. And another was a standard regression model. We actually eventually went for the random forest model because it had a slightly higher prediction value. We iteratively selected the variables based on their impact in the model. And eventually, we came up with a way to predict text complexity with a 0.85 correlation. This root mean square is on a very large scale, over 1,000. And we have this 0.85 prediction based on a 20% validation holdout. So of these 350 texts, we kept 20% of those texts aside. We built the model with the remaining 80%, but we validated it on that 20% of unseen texts to find out how well the model worked. So this is a nice result. This work was published, and it turned out that 9 text complexity variables were the most useful indicators for predicting the dependent variable, the ground truth. And we can group those 9 text complexity variables by, do they relate to the structure of the text, to syntax, to semantics, or to decoding and the difficulty of decoding. That is an example in a nutshell of feature engineering, right? You take your ground truth, your dependent variable, you take the features that you're going to put in, and then you put them in a model to predict ground truth. I'm going to show you another example, but this is for essay scoring. If anyone's familiar with the NAPLAN test in Australia, they made available to MetaMetrics over 1,000 creative essays that students had written. These were students aged 9 to 15. And those essays were rated by 2 expert humans on 10 traits. You can see the traits here on the left. And you can see the human to human, this is the inter-rater reliability, if you like. And it varies from 0.7 through to 0.9 at the overall level, at the total level. When you aggregate those traits, it's 0.92. Well, can we predict these human scores taking the same approach? And I say creative essays. Some of these essays were really very creative. It's like, you know, describe a time when you were really afraid, and how did you feel, and what happened, and what did you do? So students might relate their experiences, or they might just be telling an entirely creative story that they make up themselves. So how did we do this? Well, this was back in 2014. We used several features. First, we looked at grammar and punctuation. So we looked at word frequencies, but not just word frequencies. We looked at the word frequencies by parts of speech. And we also looked at trigrams, including punctuation. So a trigram is a string of 3 words, but perhaps you have 2 words followed by a comma. Well, that would be a trigram. We looked at information content using an approach called bag of words, and a couple of approaches here. One was the bag of words with entropy. So how rare are the words used? And what's the mutual information? How much do these words make sense if they're used together? We looked at coherence and cohesion measures. And here we used a latent semantic analysis approach. So we looked at vector length. I won't go into latent semantic analysis now, but it's a way of looking at word meaning and trying to understand what is the meaning of the word. And we also looked at the angles of the LSA vectors. So how related are the words to each other? How related are the sentences to each other? How related are the paragraphs to each other? And so on. The final set of features are the ones we don't really like very much. So we call them the yucky features. These are surface features. And that's just our way of referring to them. That's not a technical word, by the way. But this is when you count things. So you count the number of characters, or count the number of words, or count the number of sentences. And obviously that's quite gameable for students. If students just know that you're counting how many words in a sentence, then they're going to write long sentences. So it's gameable, it's a bit yucky. We put it in the model anyway. Actually, it didn't make very much difference because most of the variance was explained by these other variables. And it came out pretty well. Here is the scatter plot. If you can see that, when we look at it in this table, you can see that actually the scoring engine that we developed outperformed humans in all of the traits except one, which was punctuation. But the overall total machine-to-human correlation is very comparable to the human-to-human correlations. And so this is an example of just how it works for essay scoring. Now, there is one feature in here that we found very useful, at which I'd like to tell you about, which is lexical predictability. And this feature tells us how predictable is a word given the previous word string. So let me give you an example of how this works and how it might be useful for essay scoring. We gave a task to some students. They were students in China. And they were asked to write about whether they prefer to spend a long weekend in a country farm or an exciting city. And we showed them a picture of a country farm. We showed them a picture of an exciting city with people whizzing around, doing things. The country farm picture had, cows and trees and so on. Students provided their responses to us, and we analyzed them for lexical predictability. So if it's predictable, you should be able to know what word comes next, and that would be quite a good thing. These are actual examples from essays or responses that students wrote for us. So here's what one student wrote. I would like to climb the apple trees. This was a part I've just taken snippets right from their responses just to give you an idea, but this is one sentence in her essay. I would like to climb the apple trees, pick the apples, and spy on me. Now, if it's a predictable word, you should be able to predict what comes next. If it's not predictable, then it's somehow unusual or irregular. What word do you think comes next? The answer is cows. Let's try that again. The farm will probably have, what do you think is there? Cute. What's next? Small. What's next? Towns, but you didn't guess that, right? Around it. Okay, what's next? With cows and sheep chewing the. And the answer is pasture casually. Of course, you chew pasture casually. Were I living in that cottage, I would spend a whole day. What comes next? Next to an ajar. How are you doing for predictability here? Window. Okay, and the last one is I would experience the wind. Touch my cheek affectionately. Okay, very nice. So you can see how these students were trying to use interesting expressions, use a wide range of vocabulary, but it doesn't quite sound natural. And so this is a nice feature that we find in essay scoring, particularly for second language learners. Okay, so that is the whole feature-based approach. Let me give you an introduction to deep learning models. So the studies I showed you are a little old now. Fast forward to 2023. And of course, we live in a different world and we have deep learning models available to us. We can use these for essay scoring. They're advantageous for many reasons. Here's just four. For one thing, it generalizes very well to unseen data. So when we take that feature-based approach, we train it on a particular data set, and then we have to worry, does it apply to other essays it hasn't seen yet? There are ways to overcome that. There are ways to check for that, but it's a consideration. Whereas deep learning models don't have so much of a constraint. They can be applied to different tasks, not just essay scoring, but all kinds of tasks. The deep learning models use contextualized word embeddings. So they're much better at establishing the difference between a riverbank versus a financial bank, for example. And they incur less problems with out of vocabulary issues. So if your vocabulary is not in your training set, but it's in a new essay that you're scoring, but that vocabulary hasn't been seen in your training data, a deep learning model will be able to overcome that much better than feature-based models. We have transformer-based, so most deep learning models for more sophisticated purposes are transformer-based models now. And you'll be familiar with many of these transformer-based models. There are many more than are here. They are growing exponentially all the time. These are large language models with transformer-based training. And you'll be familiar with GPT or BERT, and so on. BERT is the Google model. This transformer-based model came about in 2017. It was a paper that was published by Google engineers. And they kind of rolled out this new transformer-based approach and said, look, here is a new kind of deep learning model. It's more advanced and more sophisticated than existing models. And since then, lots of people have taken this transformer-based model and develop their own large language models with them. It's doing two things here. So on the left, we have the encoding, and on the right, we have the decoding. And essentially what happens is on the left, on the encoding, it's ingesting text, making sense of that text, making it more abstract through various layers until it gets to a vector which represents the meaning of the words that it's ingested. It's abstracted it many times into a mathematical vector. On the right-hand side, it is then performing a decoding where it's generating text, it's generating language on the basis of this and producing text that represents that meaning. And I can give you an example of how it's working with a translation model. If you imagine how translation works, this is an expression in French. Okay, I haven't done French, so I haven't spoken any French since high school, I think, but this would be prendre une expression au pied de la lettre. And this sentence in French, if you put it through the encoding, it would translate each word, and it would translate as take an expression at the foot of the letter, which doesn't actually mean much in English. But if you then put it through the decoding layer, right, it would actually tell you a corresponding English meaning, which is take an expression literally, which is much closer to the spirit of what it's supposed to be saying than the literal translation. So you can see how the encoding and decoding layer complement each other, but they may be used for different purposes. Sometimes you may just want one or the other, depending on the task that you're accomplishing. The interesting thing about this transformer-based model is it improved previous models because it has attention layers, which go beyond words and sentences. It goes beyond a chunk of text that long, and can be applied to entire longer passages. And it does this by sort of looking at what comes forward before the text and after the text, and it holds those in its memory to be able to create a more coherent translation of an entire piece of text. So that's the benefit of the transformer model. GPT is known for using reinforcement learning, which is, well, they have a group of humans look at the output from the model, and then they say, well, that was a good answer, or no, that's not a good answer. Or they look at two answers and they say, this one was better. And so by reinforcing, by kind of giving feedback to the model, they can tune it and train it and make it work even better. So that's how these are just getting better and better. So what I'm saying is you'll see encoder models out there, you'll see decoder models out there, and then you'll see the encoding to decoding models that do the whole thing. So you will have heard of GPT-3 that came out from OpenAI in 2020. You may have heard of BERT that came out from Google in 2018. Well, you probably haven't heard of the MetaMetrics large language model, which is called SFRAE, We beat them to it. MetaMetrics had our own large language model in 2017. Yes, we beat OpenAI and Google to this. Maybe it didn't catch on because we didn't have a nice, cutesy, catchy name. It actually stands for Stacked Fully Recursive Autoencoder, which is a bit of a mouthful, but also we didn't release it to the public. We kept this for our internal research, things like essay scoring internally. It is not as big as BERT or GPT. And it's not a true transformer model. It's actually a recursive autoencoding model. And Jing will talk about this a little bit more in a minute. But I would like to give you an application of how we've used this recursive autoencoder model in some research that we did at MetaMetrics. And the question is, how can you tell whether a student wrote an assignment or an essay, right? Did they get help? Did someone else write it for them? Did they plagiarize parts of it or all of it? This is a big topic. It's not simply did they copy something from a source material. It's more like, did they go get someone else? Did they pay someone else to write an entire essay for them? Well, it turns out that by analyzing a baseline of the student's writing, everyone has a sort of fingerprint in their writing. It's their writing style. It's the turn of phrases that they use. There's something about the expressions that they use where you can kind of say, oh, look, this pattern belongs to this student. That's their fingerprint. And then you can compare a new essay or a new assignment that they submit to a baseline and say, was it the same person who wrote this? And that's great for detection of, is the student cheating? Is the student paying an essay mill to write an essay for them? So to put this to the test, we used this data set. This is the Federalist Papers. It is 85 essays on the benefits of the US Constitution. And it was a book that was published with 3 authors. Alexander Hamilton, you've probably heard of him from the musical Hamilton, James Madison, and John Jay. And when they published these 85 essays, they didn't tell anyone who wrote what, who wrote which essay. And so partly they were editing each other's essays. Some essays were written half by one person, half by another person. So we still don't know. They didn't like write it down somewhere secretly. So we still don't know who wrote which essay. There's a lot of speculation about it, but it's a nice data set to study. And so we've color-coded each author with a different color code here. And when we look at these 85 essays, you can see that using our deep learning approach, we are fairly sure that John Jay wrote these essays here, essays numbers 2 to 5. Hamilton seems to have written most of the first essay. And you can see the green here, we're pretty sure Madison wrote most of it. In some of these others, it appears to be half Hamilton, half John Jay. And so we have a way, by looking at the commonality and the fingerprint of the author, of how many of these essays were written by which author. There's been various research on this. The great thing is that no one can disprove us wrong, because those authors are not around anymore. So we stand by these results. We are sure we're accurate, and that is a great example of how we're using these deep learning models. All right, so I think, Jing, I hand it over to you, and I'm going to stop sharing so you can take over.
All right, thanks, Ali. Let me share my screen.
We can see it.
Okay, great. All right. So thanks, Ali, for the introduction to feature engineering approach and different deep learning models. So now I'm going to talk about a research study that we applied both approaches to develop automated essay scoring models. So the data set we used came from a young learner test called British Council Primary English Test. that has just been launched. And it is an AI-powered digital 4-skill assessment that MetaMetrics designed, developed, and validated for British Council. We developed both speaking and writing automated scoring models, but here I'm just going to focus on the writing models only. So I think for test developers, this should be very familiar. So before we develop any tests, we always start with the construct definition. So because for this British Council primary English test, we focus on young learners aging from 10 to 12-year-old globally in different first language speaking background. So because most of their CEFR levels would range from pre-A1 to B1, maybe mid to high B1 at most. So we want to define our construct to the writing proficiency for everyday life rather than academic English. And then after defining that general construct, we break that down into context and situations, tasks and communication functions, and the linguistic skills. So for context and situations, we would need to think about, in what kind of context students need to use their English ability for everyday life. So some of the context would be like writing emails or writing notes, etc. And then in terms of tasks and communication functions, it will be about, they will be able to use English to write about their likes and dislikes, or they state opinion and then justifies the opinion. And then to enable them to perform these tasks and communication functions, they should be able to have control over simple elementary vocabulary, or be able to use some simple grammatical structures and routines correctly, and also be able to organize information coherently to support their opinions. So that is how we define the construct. And then to be able to elicit the evidence that allows us to make inferences about students' everyday writing ability, we decided to include 3 different task types to elicit writing at different lengths and also performing different language functions. So these 3 task types are read and recall, text message, and then describe pictures. So for read and recall, we asked the students to read a very short passage. We carefully control the length of the passage so that the working memory will not be a confound that impacts students' scores. And after students read the passage will disappear. And then students have to summarize in writing what they just read. And then for text message tasks, students have to participate in the task that simulates the everyday task of sending a text message to a friend. So we have a chat bot that would present different questions to test takers, such as, hey, the weekend is coming. Why don't we go out and do something? What would you like to do, etc. And then students have to respond to the chatbot questions by writing a short text message. And then picture description is an open-ended task that asks students to look at pictures and then describe what is happening in a picture. Or they compare 2 pictures and describe which picture they prefer and why. So these 3 task types would elicit students writing ranging from 1 to 2 paragraphs to longer writing 3 to 4 paragraphs, different language functions and different genres. So another aspect of operational the construct is to design the rating scale. So this is the framework that we followed to make sure that the rating scales are aligned with our construct definition. So we start with our definition of the construct and the characteristics of the tasks, and then operationalize that into the language of rating criteria. So as you probably know, that involves a lot of simplification of the languages, distilling standard language into rating rubrics that are very easy to understand for raters. And then we would analyze students' responses and to make sure that the rating criteria can actually capture the characteristics of the student responses. We also conducted a band separation analysis to make sure that student responses can be separated into bands. And we also conduct a language review with our raters, make sure that they can understand the rubric language very, very well and apply that easily. And finally, we conducted a multifaceted RASH analysis to evaluate the reliability, dimensionality, and the separability of the rating scale. So after going through this process iteratively and refine the scale until we are very satisfied, we came up with this rubrics. And the rating scale has two traits, task completion and the language use. And each trait has 5 different score bands from 0 to score point 4. And each of the score point roughly corresponds to a CFR level, ranging from pre-A1 to B2. And then for task completion, we focus on evaluating how well a student can accomplish the task, to what extent they can provide elaborated support to justify their opinion or preferences. And then for lexical grammar, we evaluate students' control of language at the vocabulary, grammatical, and discourse level. So after the tasks and the rubrics were developed, we piloted the test items on a sample of more than 2,000 students from 13 different first language backgrounds. And all of these students are within the target age group, ranging from 10 to 12-year-old. And we did a train and test split based on the criteria that the score distribution across train test set needs to be comparable, and all of the first language backgrounds need to be equally represented. So we plotted out both the histogram as well as the descriptive statistical table to make sure that we meet these 2 criteria. And this is a visual representation of students' L1 distribution from the train and the test set. And as you can see here, in the training set, the L1 distribution is representing the availability of sample in our entire population. So we have a lot of Spanish speakers participating in the field test. That's why here you can see they are overrepresented in the train set. However, in the test set, we rebalance the data set so that all of the language backgrounds are equally represented. And this will ensure that our AES models would not have any bias because of the sample size issues. So after the student responses were collected, they were scored by human raters. And then, as I explained before in our rating scale development process, we conducted multifaceted RASH analysis and then examined rater fit statistics to ensure that all the raters can apply the rating scale consistently. So here, if we focus mainly on the infit mean square statistics, we can see that for most of the raters, with exception the first row, R4, rater number 4, the other raters have infit statistics that are very close to 1, which is the desirable goal. And for rater 4, if we look at the number of responses that he or she scored, they only scored about 20 responses. And that's why we think that caused the low infit and outfit statistics. So after we collected the student responses and also have them being scored by humans, we employed 2 different modeling approaches. So the first approach is the traditional ridge regression approach. So we started with a set of features, and then we trained a ridge regression model to predict human scores. And then the second approach, we adopted a deep learning approach. So we used the pre-trained language model, BERT model, as the initial assay representation. And then we fine-tuned the model on the assay training set. And then I'm going to explain each one of these in detail. So first, let me start by explaining why we chose ridge regression among all of the linear, highly explainable models. So we prefer ridge regression because it is a model tuning method for data that usually has multi-collinearity issues. So unlike other types of regression, such as ordinal logistic regression, ridge regression would allow us to input some of the to add in some of the regularization factors so that it prevents the model from relying too much on one or two features. And also because all of our data was normalized, so the coefficients of the ridge regression model should be consistent with the permutation importance of all the features. To be able to select the features that can predict both lexical grammar and task completion, we adopted a combination of a statistical approach and a construct relevant approach. So for the statistical approach, we started to select the feature using a greedy algorithm. So we start just with one variable, and that variable would maximize the performance on the training set. And then after that first feature was selected, we would add a secondary feature that complements the first feature. And we would add some proprietary features here so that our model does not have problems of overfitting. And we would continue this process until the model performance plateaus. So that's the statistical approach. And then for the construct-driven approach, based on our past experience of building AES models, we know that some of the features are really construct relevant. That's why we force in these features because of their construct relevancy rather than statistical power. And then to build models for these two different traits, we tried different approaches, prompt generic and prompt specific. So for language use, we chose to use prompt generic because we find out the same model for language use can be generalizable very well across prompts. But for task completion, we chose to use prompt-specific model because we compared the model performance of prompt-specific model and prompt-generic model. And we found that prompt-specific models actually have higher performance than prompt-generic models. And then after we built the models, we evaluated the model performance by comparing machine-human agreement statistics to human-human agreement statistics. And here we are not just focusing on correlation R. Rather, we looked very comprehensively at all of the metrics to evaluate machine performance, including QWK, quadratic weighted kappa, PA stands for percent agreement, and then root mean square error and the mean absolute error. And we examined that for different models, language use model, task completion model, generic, task specific, task completion, prompt specific model, etc. And after doing a very comprehensive comparison like this, we concluded that with this ridge regression, feature-driven approach, our machine scoring models have achieved satisfactory performance. So as we know that for training machine learning models, having satisfactory performance is not sufficient. We also need to examine the sample characteristics to make sure that the samples classified by our AES model actually are aligned with our subject matter experts' judgments as well. And that's what we did here. So we have different samples being assigned to score point 0 to 4. So if we examine the characteristics of the responses here, the lowest scored response, score point 0, is a very generic off-topic response, I don't know. And then for score point 1, students use isolated words and phrases. So that's characteristics that's usually demonstrated by A1 test takers, writers. And then if we look at score point 2, we would start to see simple use of sentence structures, but the sentence structures are kind of flowing through like a list rather than being coherently connected together. And then at score point 3, we would see a progression of ideas, but without much use of discourse connectors. And then at score point 4, we would see a very coherent, clear organization of a letter. So that's how we examined these essays to make sure that the scores assigned by machine are aligned with our subject matter experts' judgment. And then in addition to that, we also looked at the list of features that are supporting, that are predicting each of the trait scores, and just to make sure that and verify that they are actually construct relevant. So some of the top features that I circled here are the very popular features in our feature toolkit. And if you look at them, they are usually global features that captures the words used in context, or the global linguistic acceptability of sentences, rather than focusing on those yucky surface features that Ali mentioned at the beginning of this talk. So for example, language use, our top predictors are semantic support mean, which measures how closely a word is to all of the previously occurring words. And then we also have log linguistic unacceptability, which is a deep neural net that's trained on sentence embeddings and as a prediction of how linguistically acceptable each sentence is. And then for task completion, we have feature like top 20 n-grams, which evaluates the extent to which the n-grams of a target response overlaps with the n-grams of the top scoring responses. So after examining these features, we concluded, our subject matter experts concluded that all of these features are indeed construct relevant. So that's how we trained how we trained the AES model using feature engineering approach, and also how we validated it using subject matter experts' judgment. So next, I'm just going to quickly switch to talking you through how we trained a BERT model to predict human scores. So our engineers affectionately labeled this machine learning pipeline as AutoBERT, because everything can run automatically and they don't need to touch it. What we mean by AutoBERT is that it is a generalized natural language processing pipeline. So it uses BERT embeddings or Roberta embeddings if you are training multilingual models. And then we layer over a transfer learning task as one of the downstream tasks to fine-tune the parameters. So this ML pipeline allows us to quickly train and deploy our models for very different downstream tasks, so that we can do everything very, very efficiently. So what are some of the unique features of our AutoBERT pipeline? So first is it is producing probabilistic output. So what I mean by that is it does not just produce a point prediction, rather it segments score points into bins, and then it estimates the probability to which a response falls into different bins. And then it produces a final probability estimate by aggregating probabilities across these bins. And then the second most distinguishable feature is the pass-through feature, which means that it's kind of similar to the idea of ensemble models. So we can take the output from one AutoBERT models and use that as an input for another downstream tasks, so that we can improve the model performance that way. So that's two distinct features in terms of the modeling aspect. And then in addition to that, we can also produce a lot of analytics and rich graphics. And you can see here some of these you are probably very familiar, like scatter plot, loss functions, heat maps, etc., that allow us to examine the model performance. And then on the top right corner, you can also see that this is a screenshot that our models can provide granular feedback to students' writing. This is just raw output from the MATLAB interface used by Steve. So as some of you probably know, MetaMetrics is mostly a back-end provider, so we do not really spend too much effort, beautifying the UI here. So that's the granular feedback. And then in addition to that, the code is really short and easy. So we just need to use a wee bit of code, and then we can train and deploy very, very quickly. So that's the features of the AutoBERT models. So how does the model performance look like, especially compared to ridge regression? So we compared AutoBERT with ridge regression side by side on the criteria of correlation, percent agreement, quadratically weighted kappa, etc. And as you can see here, AutoBERT actually can perform quite well in comparison to ridge regression, which makes us feel like we have extracted all the information we can from the data set using the ridge regression approach. So based on this research study, we conclude that using deep learning approach and feature engineering approach, we were able to accomplish comparable performances. Of course, deep learning models are more time efficient because we do not need to do any feature extraction and feature selection. But the problem is if there is any results that goes unexpected, it is very difficult to root cause what it is causing it because we don't know what features actually go into the deep learning models. So that's why we think that it is very important to account for the different elements to build a validity argument for an AI-powered test. And here I would like to introduce you all to the theoretical assessment ecosystem for digital first assessment developed by Duolingo because they are the sponsor. Just joking. I really love that paper. That's why I cited here. So this is a coherent, comprehensive framework that highlights the importance for examining the digital affordance of AI-powered tests. So the component that is most important, of course, it is the transparency and explainability of the models. So this includes not just the features, but also the relationship and the structure of the test scores. We have to make sure that we are not just evaluating models based on how well they actually agree with human scores. We also need to make sure that all of the features are actually construct relevant and the structure of the scores are aligned with our construct definition. So I think Duolingo's digital first assessment framework also aligns very well from the processes MetaMetrics uses internally. And this is basically the process that I described just now for developing the models. As you can see here, we are not just focusing on feature selection and also validation by looking at human-to-human and machine-to-human agreement. We start this whole process by inspect the rating data, make sure that we really understand the characteristics of the tasks and the rating criteria, and then account for all of these elements to build the validity argument for this AI-powered test. So with that, I think we conclude our talk.
Thank you both very much. We do have a few questions that have been submitted. If you have a little time for some Q&A, I think I'll just read them in order if you're ready, and either of you respond, whoever's ready. The first question that we have is, how did you choose the human raters to get to ground truth? Did you ask them to use any specific criteria?
Sorry. I think maybe let me start first, and then if I miss anything, Ali, feel free to chime in. So if the question was regarding the British Council primary English test, we used a very rigorous process to select human raters. For example, they've got to have experience teaching English in foreign language context. And ideally, they've also have test administration experience, if not test scoring experiences. And then we have to calibrate them, make sure that they can use the rubrics consistently. They have to pass a qualification test in which they independently rate a sample, a selection of samples. And only after they pass the qualification test, they are able to score our samples.
And thank you, Jing. And I see that question actually came in at 1:41. So it was probably asked while I was talking about the text complexity study. So those 90 raters were teachers of the target students that would be reading the text. And they were just gathered through word of mouth and an email blast out to get teachers from the relevant domain who would know what their students were capable of. That is published, that paper. The title of the paper is Examining Text Complexity in the Early Grades. The first author is Jill Fitzgerald, and it's in the journal Phi Delta Kappan. Phi Delta Kappan, Examining Text Complexity in the Early Grades, if you want to check out that paper.
All right, I've got another one for you. I think I'm just going to hop around a little bit. Here's one. Deep learning models often take a fair bit of hyperparameter tuning, such as regularization, learning rate, class score balance, etc. Did you spend any time searching for the best hyperparameters for your BERT models?
Yeah, that's a great question. So one of the unique features of our AutoBERT is we use a dynamic approach to fine-tune the hyperparameters. So the learning rate and the dropout rate are actually automatically chosen to be able to optimize the model performance. So that's why we think that it's very efficient compared to feature engineering approach. It takes a lot less time to fine-tune these hyperparameters than selecting those features.
Got another BERT-related question that I'll ask next, which is, what does the granular feedback by BERT that you use look like?
Okay, let me pull up the slide. I can try to explain it a little bit. Just give me 1 sec. So if you can see the screenshot here, we have texts that are highlighted in different colors, red and green. So for the red part, that is the part of the text that was judged by BERT as having high grammatical ambiguity. And then the green bits are the ones that are low grammatical ambiguity, means the grammatical structures are used pretty well. And then we also have some brackets, which shows that these are misspelled words that, you know, so they were put into brackets by BERT. And then we also have the width of the underlying line here. That also shows to what extent the discourse structures are actually to what extent the text is actually structured coherently. So it's not very UI friendly, but I think our engineers put in some thoughts using different symbols to represent different features of the feedback.
Okay, I'm going to hop around. I'm going to ask another. Let's see. I wonder whether features engineering is more suited to certain tasks in language assessment and deep models to other tasks. What's your response to that?
I'll give a go first, and Ali, feel free to add more if you like. I think based on our past experience, it's really the client's requirements. So for most of the clients, they want transparent, highly explainable models because they want to see the connection between the text features, the rubrics, and then the predictors in the model. So we usually pass the training set through AutoBERT just to get a baseline performance. And then we use feature engineering approach and then compare that feature-based model performances with the deep learning models just to see whether we can beat the baseline. So that's the way we approach it. And then for some of the other tasks, such as anomaly detection, which is detecting outlier responses, such as a response that is completely off topic, that uses foreign language words, etc. We usually use deep learning approaches because it's very hard to find a set of features that can predict the anomaly flags very well.
Yeah, I would add, there's a role for both of these things, and if you are running an assessment and you want to have very explainable models, you've got to go for the feature engineering because it helps you explain that to your stakeholders. If you're not so concerned about that and you prize accuracy, you can afford to go for the deep learning approach. But I think as Jing is saying, there are places for both of these, and it need not be an all or nothing approach. There may be a part of this where you're using your feature model for certain purposes and your large language model for other purposes, just to get the best possible information back to your students.
And here's another question about the models that you used. So generally the performance bias of large language based models, LLM models, is a bit difficult to control. Were there any findings along this line of your study?
I'm not quite sure what the question is getting at. Could the person that asked the question elaborate a little bit more about what you mean by bias is a little bit hard to control?
Can you follow up in the Q&A to clarify your question? Bias against different demographic groups is the question. Is that a factor that you ran into, and how'd you cope with that?
So I think one approach that we applied is to make sure that we have we rebalance the data when we train the AutoBERT models. So that means that we are not oversampling responses from a certain language background, but we actually rebalance that to make sure that we have relatively equal representation from different language background. So that's one way to do it. And then another way is, this was a little bit time ago, I think we trained the models by including all of the samples in the training set, and then having one model, and then we separate them out by L1 group, and then build separate models. And then we compare the L1 specific model with the L1 generic model to evaluate the bias as well. So that's another way we evaluated that. I'm sure that our engineers have tried other approaches as well, but on top of my head, those are the two primary measures that they have used.
And I would add that this problem is not specific to large language models. It's also there in the feature engineering, and it's also there with human ratings, right? And it's probably a worse problem with human ratings than with an automated approach, whether you go feature-based or large language model. And so, I think you have to check for bias in various approaches, whether or not you're doing human scoring or AI scoring, and also on the kind of AI scoring you're doing. We also check for bias when we're doing feature engineering, we check for bias at the feature level as well. And so it's not just the overall model outcome, it's well, do these features vary across the different languages, the different language backgrounds of the students?
Thank you. Okay, I'm going to go back to the list. I'm going to hop around a little bit. One question is, what are emerging ways in which these technologies are being used in language assessment, and what challenges do they pose?
That's like a 3,000 feet question, Ali. I think
So
you
just
should
take a few minutes to respond.
you should take it.
I was hoping you'd start, so I would have a few seconds to think about it. I mean, wow. So, we MetaMetrics, Duolingo, and some others. We had a symposium on this at LTRC, and it was how are these new AI techniques and deep learning models being used in language testing across the whole assessment cycle? And so you can start from item development and generation of items using generative AI, establishing establishing theoretical difficulties of items using these techniques as well. In your test administration, and Duolingo have a presentation on this, looking at students taking the test remotely and using facial detection features to establish might they be doing something shady during the test other than being fully engaged in the test itself. And then obviously the scoring and the validation. And so it's the entire test dev and assessment cycle. It's coming in. If we're talking about language testing, where this is going to have an impact, it's not just going to be the scoring, it's going to be everywhere. Did I give you a few seconds to think, Jing, about what you want to add to that?
Yeah, but in spite of the fact that we can automate a lot of these processes, it is still very important to keep humans in the loop and check the items generated by AI and also the scores generated by machine learning models, just to make sure that they are actually explainable and they are aligned with human judgment.
I'll ask maybe just another. I know we're getting on in the afternoon, but I've got one more question for you that I thought was interesting. Would the increasing use of AI to assess writing reduce the range of writing styles human writers may have? They're not sure if it's biased, but notice that the AI generative tools tend to keep a single, very standard and not quite natural. Would that affect text classifying of these tools in writing assessments?
To reread that question. Would the increasing use of AI to assess writing reduce the range of writing styles human writers may have? So I think you're asking, as we use the AI generated text more, is it going to kind of have a feedback on the students that they start to write like the text that they see being produced? Or if they know it's being scored by these models, are they going to start to write in a way that they think will get them a higher score? I mean, sure, we have to be very careful about what we say to students in terms of how the AI scoring is working. If they detect that just writing more is going to get them a higher score, then they're just going to write more, thinking that that will give them a higher score. If they think that larding their writing with low frequency words is going to get them a higher score, then they'll do that. I think, and there's a debate about this. I think we need to focus the students on the rating scales and the standards that we expect. And then we need to make sure that our models really are assessing those standards. And so we only want them to be looking at those standards or rating descriptors as their guideline for here is good text, here is here's an answer that's inadequate, or providing them examples with descriptions of texts that meet the criteria or don't meet the criteria. What's happening in the model underlying that we can explain and reassure that these are working well, that they're well validated, and so on. If we're taking a feature-based approach, do we really want to go to our students and explain each feature that we've got in our model? Probably not. That will detract from the overall task that we've got in mind for them. If you're talking more broadly about, hey, how is the whole generative AI text going to affect society and change the way we collectively write? That question's too big for me. I think we're some way off having to worry about that.
That's fair enough. Well, I think it's time to call it quits. I know I didn't get to all of the questions there, but we do appreciate it. And once again, this will be recorded. I mean, it's being recorded. It will be uploaded to our YouTube. I'm just putting that in the chat. Once again, you can find the recording for this and the other webinars we've had in the series. Thank you. Thank you, Alistair and Jing, for joining us. Anthony, anything
Yeah, thank you very much. It's a very engaging talk and discussion. I wish we could have gone on, but it's Friday afternoon, so it's time to do something else. Yeah. All right. Thank you very much, Ali. And
thank you very much. Yeah.
Thank you.
Enjoy your weekends, everybody.
Yeah.
Thank you.
Bye.